Solvation through micellization. So, special conditions are found in solution of large cations and anions possessing a long unbranched hydrocarbon chain. For example, salts of carboxylic acids, long chain alkyl sulfonates, and long chain tertiary amines. So here the number of the repeating units must be greater than 7 in order to make the molecule amphiphilic, which means that the molecule is acting as schizophrenic, like one end is polar and the other end is non-polar. So the amphiphiles represent the presence of distinct polar and non-polar regions in the same molecule, and salts of such large organic ions are often highly aggregated in dilute aqueous solution. When the concentration of this salt of organic ion is increased within the solution, the resulting structured aggregates are formed that are termed as micelles, which are stabilized by the counter ions that are localized within the periphery of these micelles by Coulombic force. So this kind of micelle represent the formation of spherical micelle by an anionic amphiphilic molecule, and this kind of assembly is usually formed between the polar solvents, as the polar ends are directed towards the polar solvent, showing the intermolecular forces with the polar solvent, but when the same amphiphilic molecule is dissolved in a non-polar solvent, the inverted micelles are formed. So here we have a structure of inverted micelle when we use the amphiphilic molecule in the non-polar solvent, and in this case again the micelle is being stabilized through the Coulombic force of attraction between the counter ions and the polar heads of these amphiphilic molecules. Now let's discuss about this micelle. The hydrophobic part of the aggregated molecules forms the core of this micelle, while the polar heads are located at the micelle and polar solvent that can be a water interface, that is known as polar head group water interface or the micelle water interface. These kind of micelles usually have average radii of 2 to 4 nanometer, containing 50 to 100 monomers that are these amphiphilic molecule, and these kind of micelles are usually absorbed in aqueous solutions, and their geometrical structure is usually roughly spherical or ellipsoidal, whereas in non-polar solvents the micellar structure are generally the inverse of those formed in water. In these solvents the polar head groups form the interior of the micelle, while the hydrocarbon chains are facing towards the non-polar solvent, making the non-polar micellar interface. So for this kind of micelles the interface is non-polar, whereas for this kind the interface have a polar boundary. At lower concentration or the dilute solution, the amphiphilic molecules act as strong electrolytes. For this kind of electrolytes, by increasing the concentration, the specific conductivity of the solution increases, and the concentration of the electrolyte or amphiphilic molecules solution must be lower than 10 to the power minus 4 to 10 to the power minus 2. After that point, the trend of rise in specific conductivity of solution with concentration is changed, and this turning point is known as critical micelle concentration. That is usually observed around 10 to the power minus 4 to 10 to the power minus 2 mole per liter concentration of the solution. And at this point, which is known as CMC or critical micelle concentration, spherical aggregates are formed, and by increasing the amphiphilic molecules or the concentration of the surfactant, the molecules are known as amphiphils or the surfactant. The concentration variation is showing the less steep slope as compared to the steeper slope that is observed before the formation of micelles. So by increasing the concentration of amphiphilic molecules, two effects are observed. Number one is the increasing amphiphile concentration leads to an increased ionic strength of the aqueous bulk solution. So the increase in the concentration of amphiphile results in increase in ionic strength of aqueous bulk solution. And thus this phenomena is decreasing the electrostatic repulsion between the head groups due to screening of their negative and positive charges. So here we have pictorial description that when the concentration of the amphiphile molecules is increased, the repulsion between the two head groups are being screened by the counter ions. And the second observation is for the hydrocarbon tails which are making the hydrophobic part of this amphiphilic molecule. For the hydrophobic part, an increase in concentration of the amphiphilic molecules is unfavorable. Why? Because of the formation of new hydrophobic water interactions that is increasing. As these hydrophobic tails are surrounded by the solvent molecules, so by increasing the concentration of the amphiphilic molecule, the hydrophobic parts is showing repulsion that is increasing with concentration with water, and whereas the attraction between the polar heads is increased, that is because of the screening that is balanced by attraction between the counter ions, and thus result in the ionic strength of the solution containing amphiphilic molecules with increase in concentration. So if what if we increase the concentration of the amphiphilic molecule in water further? So there are two scenarios. The first one is macroscopic phase separation. That is observed due to the driving force for dissolution of amphiphile with the complete balance of the forces working against the dissolution of hydrophobic tails. So here it is observed that the driving force for the dissolution of amphiphile that is coming from the increase in ionic strength of aqueous bulk solution due to increase in the concentration of amphiphile, that is due to decrease in the electrostatic repulsion between the head groups due to screening of their negative and positive charges, is actually working against the dissolution of hydrophobic tails. Why? Because hydrophobic tails have inverse properties as compared to the increase in ionic strength of the solution. So overall increase in the concentration of amphiphile is increasing the ionic strength of the solution, and thus it is working against the resolution of the hydrophobic part. That further result into two scenarios, in which first is given here, that is known as macroscopic phase separation. That means formation of aggregates of infinite size. And the second scenario is stabilization of the solution through formation of many micelles, which are actually aggregates of finite size. And such finite aggregates are thermodynamically stable, also known as microheterogeneous supramolecular species. So we can say that the micelles are actually aggregates of finite size that are thermodynamically stable and also known as microheterogeneous supramolecular species. So in this way, through the formation of micelle, the amphiphilic molecules are dissolved within the solution with increasing concentration, and the micelles are characterized by the calculation of the CMC, that is the critical micelle concentration, and the micellar aggregation number. So as we have discussed that for average micelle that is spherical, average 50 to 100 monomers make one micelle aggregate, and this number is known as micellar aggregation number. So the CMC and micellar aggregation number depends on hydrocarbon tail length, the nature of the counter ions, and the ionic strength of the bulk solution. Now let's consider an example of amphiphilic molecule that is known as SDS, or sodium dodicyl, which is the most common surfactant have been used for the study of solvation through micellization or micellar solvation and different other studies. So for this kind of surfactant, the CMC observed is 8.1 millimolar, whereas the aggregation number is 62, means the micelles of this SDS surfactants usually have 62 monomers in the micelle. Another important surfactant is CTAB, and here SDS and CTAB are usually used for the synthesis of nanoparticles that are based on the synthesis of nanoparticle through sol gel methods. CTAB is actually the hexadecyl cetyl trimethyl ammonium bromide, and for this surfactant CMC value is 1.3 millimolar and the aggregation number is 78. If we observe closely that the first example of the amphiphilic molecule is anionic, because the long chain is attached with an anion, and the C-tab is cationic surfactant or the amphiphilic molecule, in which long chain hydrocarbon tail is attached with the cation polar head. So this cationic polar head is actually the tertiary amine or tertiary ammonium cation. We can also have amphiphilic molecules having no charge but having polar and non-polar ends, like hexaoxyethylene dodecanol is a kind of non-ionic surfactant showing CMC value that is 0.09 millimolar, which is far less than as compared to the anionic and cationic surfactants. That is due to these longer hydrophobic parts showing higher strength of hydrophobic repulsion. The fourth category of the surfactants or amphiphilic molecules is known as zwitterionic. It means that the surfactant molecule containing both the negative and positive parts. So here we have an example of the zwitterionic surfactant, that is actually known as Sb12 surfactant. The IUPAC name is given here, and this kind of surfactant gives the value of CMC is 3 millimolar, that is a bit higher as compared to the non-ionic surfactant. That is due to the self-stabilization of this molecule, but it also have hydrophobic repulsion with the solvent. So overall the type of the nature of the counter ions which are already present in the chain of this zwitterionic surfactant. So here we have described the static picture of the micelle formation, but in reality micellar systems are more complex than is implied by the simple static picture. So this description of the micelle is actually given by Harley. So the realistic picture of the micellar structure is given by the Manger. He gave the porous cluster or reef model. So here I tried to make the porous cluster in which the polar heads are surrounding like a ball, which having the polar heads at the surface and the interior is occupied by the longer non-polar chains. And if we ignore the shape of the polar chains, that is making the interior of the porous cluster like a sponge. So here I tried to make the 3D picture of the micelle, which is showing the spherical bodies that are actually the polar heads, and this one is the regular micelle structure, which is showing the rugged dynamic surfaces and water-filled pockets, non-radial distribution of chains, random distribution of terminal polar heads. So these polar heads are not stable, they are changing position within this micelle, and this micelle may have a spherical or ellipsoidal or any irregular shape in which the polar heads are randomly distributed. And here is the structure of the inverted micelle, which is showing the interior of the polar heads, and the exterior is actually the non-polar chains. In fact, a micelle is a highly disorganized structure with multiple bent hydrocarbon chains. So these hydrocarbons are not in regular arrangement, rather they are showing the disorganized distribution of hydrocarbon chains within this micelle, making the core of this micelle. And this micelle can have the cavities having no distribution of any kind of amphiphilic molecules, and even hydrocarbon water contacts. Like here I have try to show. So all these kind of deviation actually shows the deviation from the precise spherical shape. And in real, a micelle is a dynamic molecular assembly which exists in equilibrium with its monomer. So these monomer molecules tend to uh, move within this micelle, and the unit of this micelle may leave this aggregated structure. So there is an equilibrium between the micelle and monomeric forms. So at a time one monomer retains within the micelle for only 10 to the raised power minus 8 to 10 to the raised power minus 3 or 1 millisecond. After that it is replaced by another micelle, which is formed by distribution of new monomers. So the monomers units both leaving and entering the micelles make this micelle a dynamic assembly, and the duration at which a monomer remains in the micelle is depend on the length of the surfactant molecule. So these micelles are important for the dissolution of different species that are insoluble in particular solvents. So the existence of micelles in solutions of large ions with hydrocarbon chains is responsible for the observation of that certain substances normally insoluble or only slightly soluble in a given solvent dissolve very well on addition of surfactant, that is also known as detergent. So this phenomena is known as solubilization. So using solubilization we can dissolve the unsoluble substances into the permeable solvents using the surfactants. For example, if we have a non-polar solute, so let's we have this non-polar solute that is insoluble in water, but when it is dissolved in the presence of micelles, the non-polar chains will surround the non-polar solute, directing the polar heads towards the polar solvent, that is water. So in this way the micelles or the surfactants can dissolve the non-polar solutes to polar solvents, as well as the polar solute to non-polar solvent, making structure like shown here. So this phenomena known as solubilization implies the formation of thermodynamically stable isotropic solution of normally slightly soluble substrate. So these slightly soluble substrates are known as solubilizate, and the surfactant molecules which are making the micelles are known as solubilizers. Non-ionic, non-polar solubilizers such as hydrocarbons can be trapped in the hydrocarbon core of this micelle, thus make it to get solubilized. This is because of the fact that the micellar interior is not a rigid structure, but it is mobile, which means that it can incorporate any substrates. And like micelle formation, solubilization is a dynamic equilibrium process. Again here, the number of monomer units that are entering to the solubilized micelle are equal to the number of monomer amphiphilic molecules are leaving. So the structure is dynamic. So using the phenomena of solubilization, different non-polar hydrocarbons can be dissolved in the water. So examples are, so this example is useful for the solubilization of benzene, naphthalene, anthracene and pyrene into the water using the solubilizer, that is the surfactant or amphiphilic molecule that is making micelle. And for these kind of solubilizates, 1-dodecane sulfonic acid is mostly used as solubilizer. And for the solubilization of the fullerene, that is C60, is solubilized using triton X100 surfactant in the aqueous solution. Until now we have discussed about the spherical or ellipsoidal structure of the micelles, but actually spherical micelles are not formed, but the shape of the micelle is decided by the molecular structure of the amphiphile and the solution conditions. So the shape of micelle is defined by the type of molecular structure of amphiphile and as well as solution conditions, which are based on the electrolyte concentration, pH and temperature. So the structure of micelle is not essentially spherical, but it can be exist in form of bilayer structures like shown here, or this bilayer structure can make the vesicle-like structure showing the empty core that is covered by the layer of these polar heads, like making a membrane of bilayer. And the biological membranes can readily be formed by spontaneous self-association. So these spherical bilayer aggregates, which are known as vesicles, are far larger than the micelles. So in this way, using the solubilizates, we can undergo various reactions using solubilizer through the phenomena of solubilization.